Okay, I don't know how long today's going to take. I went through last night and I got some real examples of either creme chelate or Falconon reactions, and we're going to go through those. I think I have like 7 or 8, and then I think at that point we'll just call it good. And your next exam will kind of cover the synthesis we went over. I reserve the right to steal stuff off the first exam, and then the carbonyl addition stuff, and that'll be the bulk of it. So, but I wanted to give you some like real examples. Some are pretty simple in terms of like the structures, and some are a little more complicated, but they do illustrate the points. So, this first one, right? So, what you need to be able to do is you need to look at something and figure out if it's going to be cram or if it's going to like a cram chelate or like a Falconon model. So, this first one's a little different than stuff we've done before, but you'll figure it out. I have faith in you, right? So, I guess the thing we have to talk about here, and what's our group? It'll be that. All right, is if you have, so I know we didn't go over it very much in organic 1, or sorry, organic 2, but if you have an aldehyde and an enolate, right, you do an aldol reaction, right? The lone pair on your enolate comes down and attacks your carbonyl carbon, and you make, right, I'll throw a then H plus in there to protonate my alcohol, and you'll make an alcohol and a carbonyl. So it's how you can make beta hydroxy carbonyls. Oops, carbonyls. All right. So here, the counter ion for your O minus is a boron. So is boron one of the metals that chelates to make the cram chelate, or is it one of the metals that isn't able to do cram chelation? Because there's like a list of metals that are like you can do cram chelates with these, and then there were a couple that are like these don't do cram chelates. Was boron on team chelate or team I don't do chelates? No chelates. Boron was boron and ammonium salts. So like NR4 plus or boron, no chelate. So we know what the product's going to be in terms of what we're going to actually make, right? We know we're going to make this, right? But the mystery is now, what is that chiral center, right? And since it's a boron, it doesn't do a cram chelate, it does the Falcon-On model, right? So we use the Falcon-On to determine our stereochemistry, right? So like on an exam, or the exam that will exist at some point, right? If I asked you, hey, what is using whatever model or determine the product or with chirality of this reaction, right? And then like show the model, right? I want you to put the wedge or the dash, but actually then show how you figured that out. So then have to draw the Falcon-On model. So this would be Right? There's your aldehyde. Right? And then the hard part is doing the stereochemistry for the epoxide, right? This kind of looks a little silly, but you're going to say, okay, this carbon right here, right? What is blue? One, oh, no, not one. Did it again. 1, 2, that group is 3. The hydrogen is back, right? So this is R. Right, so we need to draw this in such a way that we end up with the R stereocenter on our model, right? So we know that even though it's an epoxide, right, we said that the group that has the greatest desire to be orthogonal to the carbonyl was like a methoxy. Basically, methoxy was a stand-in for an ether, right? And epoxide is just a cyclic ether. So the oxygen there wants to be orthogonal, right? And then we can kind of fudge it a little bit and say, well, here's the carbon of the epoxide. So this carbon right here is kind of that guy there, right? And then like you can draw a long line. There you go. There's your really ugly epoxide. It gets the job done though, right? And then here's your hydrogen. And we're going to hope that I did this right. 1, 2, 3, right? So if we're looking down on it, it should be R, right? Right, because it's 1, so it's 1, then it comes back towards me, 2, then over and away. So that is, if you're looking down on it clockwise, and that puts the hydrogen away from you. So that's how it should look, right? And then on the back, you don't really need to draw out the other stereocenter. It doesn't really matter, right? But that's the other carbon. So now your nucleophile, right, which is our boron butyl guy, that's going to attack along the Berge-Dennis angle, kick up, right? And that's going to lead to, again, we're going to push our oxygen and our hydrogen over, kind of away from where we put the nucleophile. So they're going to end up like this. Right, the nucleophile is going to end up over here. So like between the hydrogen and then the other group off of the model. So here's my, again, crazy looking epoxide. There you go. And so then this is, put the double bond in the wrong spot. Right, so pick a color. This carbon right here is the carbon bonded to the carbonyl carbon. So you can kind of see where it all goes together. Now we've got to get from here, right? We've got to get from this structure to figure out if we need to make our alcohol and our product a wedge or a dash. So we've got to figure out the stereochemistry on the green carbon, right? So this front carbon, we need to figure out if it's R or S, so we can translate that to the, what's it called? To the, words are hard, very hard. To the perspective drawing. All right, so we can say, all right, this oxygen is 1. The carbon that's away from you is going to be 2. Let's go back there. And then this is 3. So it's 1. We go towards the screen, towards you guys. 1, 2, 3. That should be S. And so we should have an S stereocenter. So in the end, our product should be epoxide, carbonyl, and then let's see if we have this, it's 1, 2, 3. That's S, right? Seem reasonable. Just have to make sure something doesn't look right. Did I mess up? 1, 2, 3, this, S. I'm looking at the paper and I'm trying to make sure I've matched the paper correctly. See, our model is right. Yeah, no, it's fine. It's fine. I just think they drew it a little different. Confused my little brain. Okay. Another one. Right, so this one's using a ketone. Yep. So we've got ketone and H and H. Trying to write it diol. Right, so remember diol reduces carbonyls to alcohols, right? So we're going to turn our ketone into an alcohol. That's the easy part. The hard part is figuring out what the stereochemistry should be. All right. So we don't need to draw, oh, as I forgot stuff, there you go. We don't need to redraw the whole thing, right? Because we just care about the chiral center that is like alpha to the carbonyl. So we don't need the entire ring. And like this chiral center here doesn't impact anything, right? It's just a big group. So what we can do is so right here, we just have the dashed hydrogen. So what that conveys is these two carbons here of the ring, they're in plane. They're the in plane groups. That hydrogen is back, and to not kind of have confusion, they don't draw the wedge. So this looks, our starting material kind of looks like this, right? You have an R group for all of this. You have to draw it over and over and over again, right? And then this carbon here, for our purposes, basically, it's an isopropyl. That makes sense? Right, so we just care about the fact that it's branched. We don't care that it is got a chiral center and part of a ring. So basically, we're doing this reaction off of this structure, right? You can kind of see how this is kind of a pared down, simplified version of the actual starting material, right? And that's what we care about, right? So again, we need to do R and S. That should be S, hopefully. So everyone feels good about that being S. So again, we need to draw our model. What is the group that is going to be the perpendicular group, the group that is orthogonal to the carbonyl. It's the isopropyl, right? So it's like ethers, then it's big things. So isopropyl is bigger than methyl, so that should be our orthogonal group. So we're going to have our ketone with our R group. We're going to put our isopropyl. We'll start with it over here. If it's the wrong stereocenter, we'll fix it, right? So that would leave us, let's say, this. Let's see if we've drawn it right. So is that back carbon? Let's do the stereochemistry there. This is 1, 2, 3. So if we're looking straight down, right? 1, 2, 3 should be S, right? Cool. We did it. So that's S, which matches what we said we needed over here. So then we're going to add from in this side, right? We're just going to add a hydrogen, and that should make, oops, oops, wrong button. Sorry, guys. I should put a flash warning on this lecture. All right, so O, H, R, our hydrogen's over there, H, H, isopropyl. Right, so now we have to figure out what's what. And we're going to say, right, so for this chiral center up front, the one we just made, I'm going to say that the oxygen is 1. Let's actually look at the structure. The R group is going to be 2. Is it? Yes. Yes. R group will be 2. 2. And then the group back will be 3. So now we have, right, we can think of it as like we kind of turn it on its side or turn it. So it could kind of look like OH, R group is straight down. So 1, 2, 3, and then that would put the hydrogen back, right? You just kind of twist it so that 1 comes over so the H can go back. Or you can look at it, again, if you're looking at it kind of at the side, as you like, you kind of turn your head 1, 2, 3. This looks like this should be S. 1, 2, 3, S. We'll check myself. F, excellent. So this should be the S stereocenter. Right, everyone on board with doing that? Okay, so in our product, right, we know what the product is. We just need to like put the right chiral center. Of course, we need to draw stuff better. And it should be this. 1, 2, 3. Hydrogen is at us, that makes 4. This looks like it's R, but the hydrogen points at us, so it is S. So the alcohol ends up being back. This one's bigger. So this guy here, move the box or move something. There you go. we're going to just use protecting group because the protecting group they're using is kind of obscure. So there's no super big reason to go into it. And then what is the other structure? 8. Wow. So, so they're adding these two groups together, right? And the first thing they have to do is, right now there's really no nucleophile, right? You just got an iodide and you've got an aldehyde. So the first thing they do is they treat this with tert-butyllithium. And so what's that going to do? So if you just take this first structure here and add tert-butyllithium to it. Yeah, so you do a lithium halogen exchange. You replace the iodide with a lithium. So that's going to make our nucleophile. Right. So they're going to add these two together. And again, the product, so this plus this. The product, you know what that's going to look like, right? It's a simple addition where everything stays the same except for the carbonyl. Right? And our job is to figure out what that is, right? So again, we don't have to do both entire molecules, right? We don't have to like for our model redraw the entire aldehyde, right? We can say, hey, actually, the only part of this molecule that really matters for this is I just kind of care about this right here, right? Right, I just need the groups on the alpha carbon. So again, I can kind of model the longer part of the chain is just like an isopropyl group, right? Because I can just say like, hey, OTMS, just a branch-end group, and then I have that long chain. It's just an isopropyl. So you can treat it kind of like, and again, instead of drawing the whole thing, we can treat it like just like an isopropyl, right? It's going to do the same thing, right? And then, right, we can have just, oops, did the wrong way, right? The other part of it can just be, hey, I'm a vinyl lithium with some R group on it, right? That's basically all I need to then figure out what the stereochemistry is going to be. So again, we're going to have an aldehyde. Hopefully the groups are on opposite sides now. We've been drawing. So this is 1, 2, 3. That should be R, right? So let's see here. I'm gonna guess that the isopropyl group's over here, and that's gonna put hydrogen down and methyl up there. Right, let's see if we're right. 1, 2, 3. So again, if we're looking down at it, it's going to be 1, 2, 3. That should be R, right? Because I go kind of this way around that chiral center. So I do believe I have it drawn correctly. Now my nucleophile, my lithium, otherwise blue now, my lithium is going to add right past that small group. And what we're going to get is we're going to get, again, OH, H. Here's our isopropyl. Here are 2 other groups. There's that. And then we need to set this, we need to determine that chiral center there. And we can go 1. We'll say that the vinyl group is 2, and the group back there is 3. So that looks like it is S, right? If I'm looking down on it, 1, 2, 3 is in the back. So that gets me going counterclockwise if I'm looking straight down. So we should hopefully end up with perfect. With S, so that should make this, as opposed to redrawing the whole thing, I'll just cheat and go back. That should make that a wedge, right? So 1, 2, 3. That is S, which is what I was supposed to get over there. Reasonable. So hopefully there's at least one, because when I was going through stuff last night, I was like, ooh, that problem's a good test question. So there's at least going to be one of these on the exam in some way, shape, or form. So if you feel confident in doing them. And where are the rest of my, there you go. So those are all the silicon ones. So for the cram chelate ones, I looked reasonably hard. For not magnesium ones, and I have to say I came up lacking. I got a lot of things that involved a lot of magnesium, but that's all right. Now I just have to find the examples again. Give me 1 second. Let's 43. Oh yeah. Okay. Okay. Cool. All right. Let me charge a headphone. Okay. So this one, they've got a ketone with a mom group on it with a mom protected alcohol. 1, 2, 3. 2, 3. Oops. And they add, I'll simplify it because the rest of it is pretty long. They basically just add an alkyne to it. So they add an alkyne where instead of using right, we saw how to make acetylides in organic one. They use like N-butyllithium and LDA. You could also just use a Grignard reagent. So they used isopropyl magnesium chloride, right? Grignard reagents are strong bases or strong nucleophiles, right? And a result of you being a strong nucleophile is that you're a strong base and vice versa. So this is a strong enough base that they can use this and get a magnesium on, wait, do I have, oh, I have an extra carbon. That's the problem. I'm sorry. You can all hate me now. Let me fix it. Gosh. It is not in the PowerPoint. I literally found these last night. TR. That is for TBDPS. That is for turtle. So TR equals phenyl, phenyl, phenyl. And then you got your alcohol on there. But that is TR, is 3 phenyl groups. I'll let you fix that since I messed it up. Yeah, something didn't look right. Yeah, I had a nice relaxing evening of sitting on my couch and looking up Falcon and Cram examples for you guys. Baby was like, hey, pay attention to me. And I was like, no, gotta pay attention to students. He was not a fan. He's like, they're not sitting in the swing in your living room right now. Like, that is correct. They would not fit. It would be weird. So since we have, right, our alpha carbon has an ether on it. So I guess this, and you have a magnesium, right? You're going to do a Cram chelate, right? You have that oxygen that has its lone pairs. You have your carbonyl. So now you're just going to make that 5-membered ring and have that do the work of setting your stereocenter. So, right, I'm going to take this and I'm going to flip it over. So if I can draw it right this time, right? So if we want to get the oxygen and the, oops, and the ether on the same side, like kind of in the same plane. So you can have your magnesium chloride with your R group, right? Binding that together, right, to make the ring. Right? And we have our R group over here, whatever that is. Right? And then we've got the rest of our chain. Right? DPS. So what we need to do is we need to make sure that we have the right, the right stereochemistry here so that it matches the stereochemistry that we had here. Right? So again, 1, 2, 3. That's R, right? So over here, I need to make sure that I have the R stereocenter. So if this is 1, 2, 3, if I put the hydrogen back there, right, that would be S. So that tells you the hydrogen needs to be forward. You see that? So that means that this group is going to be on a dash, And then this group is going to be, the hydrogen is going to be in a wedge. Now, when you add your alkyne, right, where your alkyne gets added, is going to want to come from the side of the hydrogen, which is going to push your oxygen back. So hopefully we end up with oxygen back, alkyne forward. Our group can kind of chill. And then everything else is good. Yeah, should be good. So there you go. And then another one. So again, like if you had a one that was clearly like a cram example, right? And I was like, what is the like use the model to show what your stereochemistry is? You would need to actually like draw the 5-membered ring with the correct stereochemistry, and then that would kind of fill that role. Right. So this other one is a really simple. These are really simple examples, but they work. Do this one. So same kind of thing. This one's, and it doesn't matter kind of what's going on with your ether, as long as your ether is just there. And then this is, oops. That's a really ugly Z. I'm sorry. Zinc. So this divinyl zinc, and they add a magnesium salt to it. So zincs are able to transfer their carbon groups. They're kind of like a Grignard reagent. So we're going to add our carbonyl, this vinyl group to make an alcohol. All right, we need to set this stereocenter. So this one's a little easier since they're kind of already drawn on the same side, right? You've got your hydrogen, oops. Your hydrogen's back, right? So what I need to do is I just need to kind of push my oxygen into plane, right? When I do that, right, if I do that third of a turn, hydrogen stays back, this group comes forward, right? Because I just push the oxygen back. The hydrogen goes from here to kind of like this, and the group that was in plane has to come forward. And again, we can check 1, 2, 3. This is S. 1, 2, 3, still S. So I didn't change anything, right? I just put them in plane. And then I'm going to have my magnesium bind those two together. And now you can see that your Grignard reagent needs to come from behind the group. right? Yeah, should come from behind the on the same side as the hydrogen. So you're gonna get why am I not able to write? Nope, don't not the whole thing. Oh god. All right, sorry, I had a little stroke. We're back though. Right, so you're gonna put the group you add on the same side. The oxygen is forward. The hydrogen is awkwardly in plane. Right, and then you're gonna have that guy. We can check our stereochemistry, see what we ended up with. Right, we'll switch the H in the double bond. So this should be 1 sec. 1 1 2 3 1 2 3. This looks R, so this guy is S. Right, because I just switched. I switched this group and the hydrogen. I get the hydrogen back, and that made the enantiomer. So I just made it the easy one to do. Because it's horrifically ugly. Hey, no, it's it's fine. It's fine. Right. So I switched. So I started out with hydrogen in plane, double bond here, right, and then you just draw it like this, right. So I started out with that. This one's hard to figure out, so I just switch H and whatever group is back. So we draw the whole thing. There you go. So now this is 1, 2, 3. So this one is R, but these two guys are enantiomers. Or those two power subs are enantiomers. So this would be S. Checks paper. Paper says it's S. We did it right. Next one. Which one was this one? One sec. Oh, there it is. I remember reading this now. Okay. So, okay. I feel like we've talked about this semester. Inorganic 2 remembers. Do you guys remember how you get from an ester to an aldehyde? So we can actually do this reaction. So we actually add to our aldehyde. We need to get from an ester to an aldehyde. One step. One reagent. I'll even remind you that that reagent likes only does this if it's cold. Like really cold. that makes diols. These are the D. Yeah. How many equivalents of dibol? Lower. 1. Right, so remember dibol adds, has a hydride that is able to add. So I'm only adding 1 hydrogen to get from ester to aldehyde. So I use 1 equivalent of dibol and I make it really cold so it doesn't reduce any further than the aldehyde. So that's how you get the aldehyde. So they had this, and then they just take this and they added vinyl magnesium chloride. Right? Again, we know what the product is without stereochemistry, right? Because you're just adding a Grignard reagent, put a little VenH plus in there. We're just adding a Grignard reagent to a carbonyl, so you know that you're going to make an alcohol, right? Since it's an aldehyde, it makes a secondary alcohol, right? So now it's just figuring out this chiral center. And again, we have an ether at our alpha carbon. So now we just have to get that oxygen and the carbonyl on the same side, right? So if we leave it in the same kind of structure, right? O, TBS. So we just have to figure out if our methyl group is forward or back. So again, right here, 1, 2, 3. Luxar is S. So we need 1, 2. So we need our methyl group forward here, right? So the methyl group's forward. That is going to be S. We're going to board with my S assessments here. Okay, so now our magnesium is going to bind those together, make our ring. We want to add our vinyl group from the same side as the hydrogen. Right. So that's going to get us not enough space. And we can make it work. No, we can't. I'm going to redraw it real quick so we can actually have the space to do it. Right, so then we add our vinyl magnesium chloride. Right, we're going to have pushing this forward, this being back. Here's our hydrogen staying in plane. Right, we'll redraw this so it's easy to do. Right. Why did I do it that way? Sorry. Right, so this should be 1, 2, 3. So this looks R. So this is S. Sure I'm right. Seems reasonable. And then one more for the road. Yeah. No worries. Oh, this one's weird. Wait a minute. No, that's fine. Never mind. Never mind. All right, so this last one is a little different, right? They're using, find the exact example. Of course, I didn't draw it out. Try to get the structure drawn right. So H, methyl group, and then we will put so they're using this silane as a source of hydride. So silicon is not one of our what is it called? Is not one of our groups that makes a chelate, right? So we're going to use the Falconon model here. So we're going to have ketone, oops, with our phenyl group coming off of it. And then let's say one, oh no, that's wrong. 1, 2, 3. So this is going to be R. So our group that's going to be perpendicular is the nitrogen. The nitrogen is kind of like an ether, right? So let's try it this way. See if we're right. 1, 2, 3. So this way is S. So I have it on the wrong side, right? So this is S. So I should have drawn it this way. And there's no shame in getting it wrong, right? That's why you check the stereochemistry to make sure you have it right. So there you go. And so we're going to add our H minus along here. So that's going to give us and then our H minus adds along here, pushes up. So that's going to give us O, H. Here's our amine. Here's that, H. There you go. 1, 2, do it like that. The group at the back is 3. So 1, 2, 3. I should be S, right? So I'm top, bottom, back. Backwards clock, we're S. So this chiral center right here should be S. So then in our product, right, which was this, Right, we're going to have 1, 2, 3. So this has to be forward. So we're S. Feel good about this stuff? Seems very doable. Okay. Yeah. So I guess we did, since the last exam, I want to just, we're going to do it this way. We did the carbonyl additions to here, and then additions to olefins. I think we did, like, we got through sharpless dihydroxylation. So somewhere around there going forward, and then anything kind of new we picked up on the in the synthesis that we went over that is somewhere in here. Yeah. So right, we did the Yamaguchi electrophilization. We did oh, what is his name? Oh, if I see the reagents, I'll remember. Oh, there it is. The Greco elimination, and then the few things that we did in there that I like kind of pointed out, but for the most part, it's going to be some stuff from there, and then the carbonyl additions. And again, 1 or 2 things might sneak in from previous stuff, but the bulk of it's going to be focused on doing the things that we've been doing since the first exam. So that's basically all I got. So I'm going to work on your exam. My goal is to have it up either Sunday during the day sometime or Monday morning, and then just give you from Monday morning till like Friday at like noonish, and then I will try to grade it that afternoon. Maybe we'll see. No class next week and no lab. Lab's done as of today. So get me your lab notebooks by the end of next week. So again, Friday at some point. If you want to give me your physical lab notebook, that's cool. If you want to give me your like pictures, the one thing for this last lab, make sure you calculate the yield of the product that we got. And then your project, use all this extra time you have next week to make sure that you get your project started or done or to a point where you're like happy with it. And then the Tuesday after break, we will meet via Zoom, and then each group will need to like walk us through how they try to synthesize their molecule. So just like the ones that I had shown you, I'm not super looking for like an awesome like looking presentation. Like just focus more on the chemistry. You don't have to like make a bunch of slides or anything. It can just be something as simple as like a piece of paper that you have drawn, or so that I can so that everyone can read it and we can screen share it and we can do it that way. So it doesn't need to be anything that you're like, you don't need to spend hours on the presentation aspect of it. Spend those hours on the actual chemistry part of it, because that's what I'm actually going to care about. I'm not like, oh, those slides weren't neat. I don't care, right? So it's more just like, does the chemistry work? Does it make sense? Did you think about things? So with that, I will be around if you guys need me, but I will see you the Tuesday after Thanksgiving.